Hello friends, welcome back. So hope you have been enjoying my videos and your concepts of physics are getting better day by day. So this video is a continuation of the previous video. In the previous video, we learned how to apply rotational mechanics by taking the help of the famous fireball scene from the movie Troy. We learned how to apply the principle of conservation of angular momentum. So in this video, we will take the same problem which we discussed in the previous video and we'll try to solve that problem using kinematics. So let's go for it. So let's try to solve this problem using kinematics. So, so as we can see, this is the fireball which has been released by the Trojan army, and as this fireball moves toward the Greek army, it rolls on the ground on the surface, and at time t is equal to 0, the initial position, this fireball has a linear velocity of v naught, and it has an angular velocity omega, which is equal to v naught by 2r. So our objective is to find out the linear velocity of the fireball when pure rolling starts. So what do we mean by pure rolling? So at pure rolling, the point of contact of this fireball with the ground will have a zero linear velocity, and as the point of contact will have zero linear velocity, there will be no friction which will act on the fireball. So as we can see, this fireball has both linear motion and rotational motion. So as we saw in our last video, whenever we encounter a situation in which the object under consideration has both linear and rotational motion, then we do the analysis in the following way. We split the motion into rotational motion and translational or linear motion, and we do the analysis separately, and finally we superimpose the results. So when we consider the rotational part, we assume that the object is rotating about its center of mass, and then we do the analysis, and we ignore that the object is having any translational motion at all. Similarly, when we consider the translational motion, we ignore any rotational motion. We simply assume that the entire mass of the object is concentrated at the center of mass, and we simply consider the linear motion of the center of mass. So if we look at the free body diagram of the fireball, we will have the weight, which is mg, which acts in the downward direction, the normal reaction n, which acts in the vertically upward direction, and the force of friction, which will act in the backward direction. Okay. Now, why will the force of friction act in the backward direction? The reason, I mean, we have already discussed the reason in the last video. Let me again reiterate the reason. So the velocity of this point P will be the summation of its velocity because of linear motion and rotational motion. Now, as we can see, because of linear motion, this point P will have a forward velocity, which is in this direction, and because of rotational motion, the point P will have a backward velocity, which is this direction. Okay. Now, because of linear motion at time t is equal to 0, the velocity of this point P will be what? V naught. Because of rotational motion, the velocity of this point P will be what? Omega r. Okay, and omega is equal to V by 2r, so omega r will be V naught by 2. Okay, so the net velocity of this point P will be in the forward direction, hence the force of friction will act in the backward direction. Now let's analyze it, the linear and rotational motion separately. So if we focus on the linear motion of this point P, the velocity of this point P at any time t will be given by v naught minus f by mt. So this is essentially this equation only, v is equal to u plus at, where u is the initial velocity and a is the acceleration. So here the initial velocity is given by v naught and the acceleration is given by minus f by m. Now why minus f by m? The reason is that if we look at this free body diagram, the normal reaction and the weight balance each other. So the net force which acts on this fireball is the force of friction F, which acts in the minus I cap in the negative direction. So the acceleration will be on this fireball will be minus F by m. So the velocity at any time t will be given by V naught minus F by m t. Okay. Now let's focus on the rotational motion. Now we know that the torque we know that torque is equal to I alpha, where I is the moment of inertia and alpha is the angular acceleration. So alpha will be equal to torque by moment of inertia. On this fireball, what is the torque which acts? Now the normal reaction and the weight, they all pass through the center, so they do not cause any torque. The friction does not pass through the center, so the torque on this fireball will be caused because of friction. Now what will be the torque? The torque will be given by force of friction into r, which is the perpendicular distance of this force from the center about which the object is rotating. So torque will be Fr divided by I. Now we saw in our last video that for a sphere, the moment of inertia is given by 2 by 5 mr square. Again, as I mentioned in the last video, you can derive this value using the using the formula for moment of inertia for continuous bodies, which is integration of r square dm. So if you integrate it over the entire body, you get this 2 by 5 mr square for a sphere. So alpha will be given by, if we solve this, 5 by 2 into f by mr. Now again, omega t, which is the angular velocity of this fireball at any time t, will be given by omega naught, which is the initial angular velocity, plus alpha, which is the angular acceleration, and t, which is time. So at any time t, the angular velocity of the fireball will be given by this equation. And if you plug in the values of omega naught and alpha, we will get omega t is equal to v naught by 2r plus 5 by 2 into f by mr into t. Okay. Now, what will be the velocity of this point P? Because of rotational motion, it will be omega t into r in the backward direction. Okay. So if we multiply this by r, we will get omega t r is equal to v naught by 2 plus 5 by 2 into f by m into t. Now, when pure rolling will start, the point of contact, which is P, will have zero velocity, and that will happen only when the forward velocity because of linear motion is equal to the backward velocity of point P because of rotational motion. So that will happen only when Vt is equal to omega t into r. So if we equate this equation with this equation, we will ultimately get Vt, which is the linear velocity of this fireball at pure rolling, equal to 6 by 7 V naught. Okay, so when pure rolling will start, Vt will be equal to 6 by 7 V naught, and this is the same result which we got in our last video where we solved this problem using the principle of conservation of angular momentum. So we have solved this problem using two approaches. So I hope that rotational mechanics would now be much more clearer to you. So that's all I have in this video. In the next video, I will come up with some other interesting topic. So thank you.